We're going to get started. I don't have anything by way of announcements today. I just wanted to remind you about this lecture series, organic lecture series. The speaker is someone who is truly distinguished in this field of distributed computing. He essentially defines things that are like the very considered to be, maybe if you take a distributed lecture computing class, you'll probably see his work in maybe the first third of the semester. So he's a big case. And there are two talks. There's one today. Talk starts at about 6, maybe. There's a reception at 5:30. There will be some sort of food or snacks, or I think if there isn't any, don't ask me. And then there's a talk tomorrow. Today's talk is supposed to be more general. It's about blockchains and how this whole technology is sprung up. Tomorrow's talk is more technical. I just found out that there's free parking for today's talk, if it makes a difference. Anyway, just wanted to advertise this. This is, general advice is if big people, big names come and visit and give talks, it's good to show up and attend the talk simply because you may not see this again because everyone is busy. Alright, I'm going to continue with learning theory today. Hopefully it's going to be the last of the learning theory lectures, and then we move on back to algorithms. Minor logistical thing, today's video is, well, we can't find the camera. So it's going to be webcam quality video. I'll post the annotated slides later on. Yeah?
Just a note about the homework I emailed you about question 22.
Oh, right. So there are two questions. There's question 22 and there's one more. Georgi is around, you can remind me. There are two questions where it turns out that we gave the wrong answers. So we've decided to give points to everyone for those two questions. There's 22 and one more. So yeah, I mean, if you find yourself with questions that where none of the answers work, or despite you knowing that the answer is right, Canvas says it's wrong, don't worry. We will fix it afterwards. Thanks. Alright, we're going to continue with learning theory. At the end of the last lecture on Tuesday, on Tuesday we looked at agnostic learning. And we were still looking at the sort of analysis of batch learning, and as I mentioned, the foundational assumption that drives the analysis is the assumption that there is a fixed, perhaps unknown distribution that generates examples, and our training set is a random sample from that. And with using only that assumption, we can define this question, the idea of PAC learnability. But in order to see the result, these two results that we saw before, basically both of them are essentially Occam's razor kind of results. We made further assumptions. The one at the top, we assumed that the true function is inside the hypothesis space. So if this is the constant class C, the hypothesis space is this. superset of that. In agnostic learning, if this was a complex class, the hypothesis space need not contain it. And in both cases, we were able to prove these results that say, if you have these many examples, then with high probability, you will be able to, your classifier that you get is going to be good enough. It's going to have an error less than epsilon. But there was another assumption that we had in place, which made life easier, but perhaps is a bit unreasonable, which is that the hypothesis space that we consider is finite. Because we are talking about finite hypothesis spaces, we are able to talk about log of the size of the hypothesis space, and essentially the result here is that learnability depends on the size of the hypothesis space. Now, unfortunately, this doesn't really cover most settings that we care about. In particular, it doesn't cover, for example, the perceptron or linear classifiers because, as I think you mentioned, the size of the hypothesis space there is infinite. So, let's see. Let's just list out all the assumptions. By the way, this is basically how theory works, right? You want to solve a problem. That problem seems very difficult to solve, so you start making assumptions till you get something that you can actually think about. And then you start thinking about whether those assumptions are reasonable. And maybe start dropping one at a time. So, the assumptions that we had were, one, fixed distribution, two, finite hypothesis. And here it was H is a superset of C, and here we dropped that assumption. In this case, this does not hold. So there were three assumptions. One of them we ignored, and we saw that we can still do come up with a learnability result. That's agnostic learning. Today, we're going to get rid of this one. The assumption that we have a finite hypothesis space and see what happens. It turns out, in order to get rid of that assumption, we need to develop, or at least we need new theory that can somehow measure complexity of functions. And that's what we're going to look at today. It's called the VC theory. And this is one of the more sort of fun parts of machine learning. Somewhat more complex parts also. But anyway, so just to kind of set the stage, we're still talking about theory of generalization. We defined PAC learning, and following the definition, we had our first Occam's razor result, and then that led to these learnability results. Some functions, some finite classes of functions cannot be learned, because you will need an inordinate amount of data. Some classes of functions cannot be learned because the computational complexity of any learning algorithm is going to be unreasonable. And then we dropped this setting that the hypothesis space contains the true function. That took us to agnostic learning here. And today we're going to drop the finite hypothesis space assumption and go to VC dimension. So the intuition that we're going to try to formalize is the idea that, yeah, sure, we have infinite hypothesis spaces. But some infinite hypothesis spaces, even within that, some of them are more expressive than others. So imagine that you want to label points inside a rectangle as positive and outside a rectangle as negative. Or inside regions as negative and outside regions as positive. So you could have inside a rectangle positive and outside as negative. Or you could have some complex shapes and inside that is positive and outside is negative. Now, the complex shape is intuitively more expressive. If you consider the set of all such shapes, it can perhaps capture more fine-grained distinctions because it allows things to sneak into these edges. Does that make sense intuitively? I mean, before we formalize anything. Our goal is to sort of capture this idea using in some sense, think of it as a certain measure over these function classes. So another example is linear classifiers versus combinations of linear classifiers. If we give you a linear classifier, you know, does not capture the XOR function. So if I have plus, minus, there is no linear classifier that captures it, but there is a combination of linear functions. If I say everything on this side is positive, and then, oh, I put the minus in the wrong place. Everything on this side is positive, and everything. Basically, think of it as the product of the bits. So if both of them are positive or both of them are negative, so some sort of combination of linear classifiers can capture XOR, whereas linear classifiers can't. So how can we get this sort of a? So what we need is some measure of expressiveness of function classes that is not the size, because the size is all infinity. These are all infinite functions. So what can we do? The answer is called the Vapnik. I'm going to try to pronounce his name. Chervonenkis dimension. I will never say the name again because I can't. It's the VC dimension. And the VC theory is, or the VC dimension is the answer to the question, how expressive is a class of functions? Just as an aside, Vapnik and Chervonenkis are really big names in machine learning. The latter is no more. Vapnik is still alive. He's at Facebook. Well, when I say he's at Facebook, I mean he works at Facebook. Not he has a Facebook account. And he, in addition to coming up with the VC theory as a direct consequence, also is the father of support vector machines and is like a giant in machine learning. So the VC dimension, it turns out, is analogous to the size of the hypothesis space. Actually, it's I'll pose an exercise question later on, maybe it will also be in your homework. For finite hypothesis classes, the VC dimension is exactly the same as the log of the size of the hypothesis class. And it generalizes to infinite things. Let's start with an example, because this is somewhat of a, this can quickly become a tricky thing, but if you go through this process systematically, it's actually not that complicated. Let's say that we want to learn rectangles. Let's say that our target function is this rectangle here. Everything inside the rectangle is positive, everything outside is negative. Our goal is to learn this rectangle using examples. And let's say we know that our target is a rectangle. So let's say we get some examples. There are a couple of positives and one negative, and maybe we learn a rectangle. Clearly, this is not the right rectangle, but it fits the data perfectly. And then we get a few more examples, let's say, and we can grow the rectangle. Let's assume no noise here. We can grow the rectangle. Still, it fits the data perfectly, but it's still not the rectangle that we wanted. We may get more examples, but maybe these examples don't change the rectangle that's being learned. And we can keep getting more and more examples. So, two questions I want you to think about and answer. Will we ever perfectly learn the hidden target function, the true rectangle that's there? Question number one. Question two, will we come close? So, what about the question one? Will we learn the rectangle perfectly?
Yeah. If you set your step size like small enough,
How small?
enough to reach that step.
But let's say you give me a step size that's small enough. Let's say you learn a big rectangle. You learn a rectangle that's really close. I'm going to zoom in here. You learn a rectangle that's something like this, or little, something like this here. And then I give you an example here. Then you grow it. You learn a rectangle that's here. Then I give you an example here. I can keep finding positive examples that are between the boundary of a rectangle and the boundary of the true rectangle. Why? Because it's infinite. I can keep dividing by 2. And you'll never get to 0. And if the goal is to learn the perfect boundary, not close approximation, but the perfect exact same boundary, will you get to it? Yeah?
I mean, I guess it depends on how you classify it, but like if you had a point on the boundaries? Would you be able to do that, like just in the corner?
Oh yeah, that's an edge case. If you had a point on the boundary, you might be able to get to it. But that's yes, that's the only. That's true. Yeah.
What if you set a margin for that?
Let's say that we don't know what margins are yet. I don't want a margin. I want exact. You can say no or yes.
No.
So the answer is no, because no matter if I care about learning the function exactly, no matter what rectangle you learn, I will find a point between your boundary and the true boundary, because I can keep dividing by half and keep getting something in between. The point here is that the real numbers are dense, and they are infinitely dense. But touching something that a lot of you hinted at, can we come close? We can come arbitrarily close. If your step size, for example, is small enough, you can come really, really close. If you are willing to concede a certain margin, you can come within the margin. You may not be able to get to the exact rectangle, but you might be able to come close. So maybe we should think about how, what really close means. Now let's think about the expressiveness or expressivity of functions. Say you have these 2 points. Now let's say you have these 2 points, and my goal, what I'm going to do, is pick an arbitrary labeling of these 2 points. I could label one of them as positive, the other one as negative. And question to you is, no matter how I pick a labeling, would you be able to find a line that agrees with my labeling? Yes. There are only 4 ways to label these things. You have circles and triangles as the 2 labels. There are only 4 ways to label these things, and no matter how I label it, you will be able to find a line that separates the 2 labels. Right? So assume that this is something like that. No matter how I label it, it's possible to draw a line that separates out the circles and the triangles. So this is the basic idea that we are going to expand into defining VC dimension. This situation, given 2 points that I get to pick, or let's say given 2 points that you pick, no matter how I label them with a linear classifier, you can separate them. What that means is that we say that linear functions can shatter 2 points. What shattering means is, no matter how an adversary labels it, you, with your function class, can find a classifier that agrees with the adversary. So the adversary cannot fool your hypothesis space for these 2 points. Okay, that's so the linear classifiers can shatter 2 points. Now let's consider a larger number, say 14. 14 points here. I counted. I think, I don't know. Let's say 14. Now, let's say I give you this label. Can you find a classifier that shatters it, that labels it correctly? Yeah, there's a line. But can you think of a certain labeling that no linear classifier would work for, would agree? Something like this. The triangles and the circles are mixed up. There is no line that agrees. I can try to place the line however I want. Nothing's going to work. So what we say is, this particular labeling cannot be shattered, which means, we say that linear functions are not expressive enough to shatter 14 points. Because if you give me 14 points, I will find a labeling for those points such that no linear function can classify it. So, if you give me 2 points, I will find, no matter how I try to fool you, you can't, your linear classifier will find a labeling, but find 14 points. I can easily find a labeling which does not agree. Yes?
Is it proportional to the dimensionality too, though? Because what if we just increase the...
In this case, it is. For linear classifiers, it turns out it is. it's the dimensionality plus 1, as we will prove in a bit. But that's the linear bit. That's for linear classifiers. Well, this doesn't mean that no function exists that agrees with this labeling, right? I can find a function that agrees with this labeling perfectly. There are more complex functions that can separate them. So what this means is that there are complex functions that can shatter 14 points. It just so happens that linear classifiers can't. Ergo, linear classifiers are less expressive than these weird squiggly things. So we can now, let's formalize this idea to define shattering more formally. Suppose you give me a set of examples. This is a finite set of examples. Let's call it S. These are fixed points. We say that, and let's say we have a class of functions, H, like your hypothesis space. Now, we say that this class of points, this set of points, are shattered by a function class if every way to label those points, in other words, every partition of those points into positive and negative, no matter how you do that, there's a function that can agree with that partition. Like think about the 2-point case. The set of points that we had were those 2 points, those specific 2 points, and no matter how those 2 points were labeled, the points were there was some linear classifier that agreed with it. So 2 points, that particular set of 2 points, let's call it S, is that point and that point, can be shattered by linear classifiers. For 14 points, those particular 14 points, no matter, I can easily find a partition of those 2 points into positive and negative that for which there is no linear classifier, so 14 points cannot be shattered. And the intuition is that a more expressive or a richer set of functions can shatter more points. Let's work through some examples, because I feel like at least this this definition can get very quickly rather complicated without an example or 2 or 3. So let's consider a hypothesis class. By the way, feel free to stop me if there are any questions, because I'm trying to build it up to something really tricky, in a rather tricky definition. So we have not yet come to VC dimensions, but VC dimensions get tricky, so stop me if there are questions. So consider this hypothesis space. We're going to call this left bounded intervals. Every function in this hypothesis space looks like this. So inputs are on the line, with positive numbers, let's say, on the line, 0 and above, and every function is basically gives you some sort of a left bound, this is decided by this number, this is some number here, and everything less than that number is positive. So this is a function here, this is a different function, and this is a different function. So all the points in this region are positive, and everything else is negative. This is a class of function. It's completely defined by 1 point, right? We call that point A. So this is a hypothesis class, and we're going to ask, can this hypothesis class shatter 1 point? So this is a line, I give you 1 point. Now, in order to start this process, we need to consider every possible labeling of this 1 point. We have only 2 labels. I can label this as positive. Is there a function that can label this point as positive? Let's say this is the number 1. What would give me an A that defines the thing? Here. 0 won't work because A should be positive. Greater than 1. Something greater than 1. I heard a 2. So 2 here. And what this does is everything inside this is positive. So this function perfectly labels the point as positive. But maybe this point was not positive. Maybe it is negative. Is there a function that assigns a negative label to this? Sure. Tell me a number. 0.5. 0.5. Everything less than 0.5 is positive and everything outside is negative. 1 is more than 0.5, so it gets a label negative, which means there is at least one set consisting of one point, which is this point here. One point can be shattered by this class of functions. Now, let's get ambitious and let's go to 2 points. One and two, or one and it doesn't matter, A and B, or let's just use numbers 1 and 2. Now we need to consider all possible labelings. Once again, so can there be a function that can assign plus to both 1 and 2?
Yes. 3.
3, something like this. I'm just going to draw the one of the brackets. Okay, can there be a function that assigns a plus and a minus? Something like this. Can there be a function that assigns minus minus?
0.
Something like this. Okay, what about minus plus?
No.
No function. Our hypothesis space cannot you cannot search as you may, you cannot find a function in our hypothesis space that assigns this particular labeling, because either both of these will be positive or one has to be, if you put it here, both will be negative. If you put it here, both will be positive. If you put it here, both of them are wrong. Right? So, this means 2 points cannot be shattered using this class of functions because there is a certain labeling, namely the one at the bottom, this one here, that fools the hypothesis class in some sense. If you gave me 2 points, any 2 points, these 2 points, let's say, what I would do is I would label them this way and say your class of functions is not good enough. So 2 points cannot be shattered, but 1 point can be shattered. So left bounded intervals can shatter 2 points, but not 1. Sorry, the other way around. Can shatter 1 point, but not 2. Right? Questions before we go to something more complex? Given 2 points, you can find a certain labeling such that no function in this class is consistent with your labeling. Okay, now if there are no questions, I'm going to make this way more complex. Arbitrary intervals now. So this time we have the entire real line to play with, and our functions are arbitrary intervals. You have a span A to B. Everything inside is positive, and everything outside on both sides is negative. Seems like the same thing, right? All you have done is move the origin to A. Seems like the same thing, but let's play the same game again. So this is what if you have A and B, this is what your function class would look like. And now I'm going to just consider all possible cases. Let's do 1 point again. So you have a real line. Let's say this point is again 1. Can you give me an A and B? That we have to consider all possible labelings. Can you give me an A and B for the first case?
0, 0, and 2.
0 and 2. Okay, that works, right? Can you give me an A and B for the second one? 2 and 3. So everything here is positive. 1 is clearly outside the range. So 1 point can be shattered. It's not just saying that this 1 point can be shattered. It turns out any 1 point can be shattered because you can play this game. So any 1 point can be shattered. So let's just write that down. 1 point. Let me just now let's do the same thing with 2 points. Remember, in the previous case, 2 points failed. So I have 2 points here, and I'm not going to give you numbers there. There are just some 2 points. Can you just consider all possible labelings again? And can you just tell me where to put the brackets in each one for the first one? Okay, I see a visual answer encompassing this. Okay, the second. Okay, somewhere here. So
Inside is second.
something like this. And here, of course, it's this one. So left bounded intervals could not shatter this, but arbitrary intervals can. So in some sense, the real intervals are more expressive than the left bounded intervals. So 2 points. So far, does this make sense? So far, any questions before we? You probably can see where this is going, right? But the reason I'm going so slow about this is because this will basically be kind of your homework questions, except it will be more difficult because you have 2 weeks. It will be more complex classes of things. So let's consider 3 points now. Can someone tell me? Let me tell you the 3 points cannot be shattered. So can someone tell me a labeling of these 3 points that won't work? Yeah.
Plus, minus, plus.
Plus, minus, plus. So for plus, minus, plus, I can try putting the brackets wherever I want. The middle point messes things up for us. So if I put the brackets like this point becomes minus. If I put the brackets like this point becomes a minus. If I put it like this point becomes a plus. And there is no way I can put the brackets so that I'll get all 3 labels right. Right? So that means 3 points. Now, notice that I did not put any numbers here. It's not just, these are 3 arbitrary points. There are no other way. There is absolutely no other way in which 3 points can lie on a plane. Because these are arbitrary not a plane, on a line. These are arbitrary 3 points that I chose, and it turns out there is one labeling that fails. It does not mean that every labeling fails. I could have come up with a different labeling, different partition essentially, something like plus, plus, minus, and this would work. But that's not enough. It should work for every way to partition the thing. So you should enumerate all possible labels and show that all of them work for this to be shattered. Shattered. Any questions? So it turns out that if you consider these things, 3 points cannot be shattered, and this is essentially a sort of you can call it a theorem if you want. And the proof of that theorem is you enumerate all possible labelings of 3 points, not enumerate all 3 point partitions. Partitions are basically labeling, right? I mean, if you have a set of things, I partition them into 2 groups, call one of them positive, the other one negative. So I enumerate all positive partitions, and I can produce one that forces this class of functions to get full. So 3 points cannot be shattered. Let's make this. Let's be brave and go to throw in one more dimension. Half spaces in a plane. Half spaces in a plane is basically just a fancy way of saying linear classifier in 2 dimensions, or which itself is a fancy way of saying a line. So we have a classifier like this. We can play the same game. Can 1 point be shattered? You can just shout out. What does it mean, 1 point? I have a plane at some point here. Yes. I could assign it as positive or negative, and I can find a line that perfectly does this. Can 2 points be shattered? Yes. Okay, I don't need to draw the axis because my screen is a plane. So 2 points can be shattered. Can 3 points be shattered?
Yes.
Let's consider 3 points. Okay. I have 3 points. Can not arbitrary 3 points. Can these 3 points be shattered?
These 3 points.
Can someone tell me, walk me through the reasoning? How many ways are there to label these 3 points? There are 8 ways, but some of them are essentially equivalent. I can label all of them as positive, in which case I'll put the line here. I can label all of them as negative, in which case I'll put the line that way. Or, as you say, one of them will be an odd man out. So let's say two positives and a negative. In which case I'll put the line in the middle and just point it this way. So, these 3 points can be shattered. But some of you said no. Why?
Three lines on the line, and the middle one is like the sign of the middle one is different.
So, something like this. So, they are on a line, and then plus minus plus won't work, or minus plus minus won't work. So, some 3 points can be shattered, some 3 points cannot. So, with 3 points, we are entering this territory where there are certain special cases where things can't get shattered. But shattering is a property of the hypothesis space and the set of points. So these 3 points cannot be shattered. 3 points that lie in a triangle can be shattered. So unlike the other cases that we saw before, we can't just say 3 points. We need to say which 3 points, because 3 points on a line, there's only one way to arrange 3 points on a line. But in 3 points on a plane, there are really 2 different ways of doing things. Either the 3 points can be on the line, or they can be forming a triangle. Okay, that's good. So, what about with 4 points? I'm going to argue that let's consider 4 points before any argument that I make. What do you think?
So
XOR cannot be classified linearly, so by extension, 4 points cannot be shattered.
Well, that's not a proof. That's an example.
Yes.
You need to enumerate all possible ways of arranging 4 points on a plane.
But some of them will
But
definitely
you choose
break,
one
right?
that doesn't.
Will it?
Why not?
Okay,
If 3 did,
3
how
did.
come 4 wouldn't? If you put them in the same line. Positive, negative, positive, negative.
So it cannot. Right? Okay, well, you had to pick.
Yeah, if 3 of them are on the same line, then you can find a way to make them separate.
Yes.
If none of them, now the 3 of them are on the same line, then we can find an XOR.
Then you can find an XOR.
Yeah.
You have missed one case, it turns out. But essentially, that's the rough argument. So, with 4 points, there are really 2 high-level cases. One is, if I have 4 points, either 3 of them lie on a line and the 4th one lies outside, or 3 of them, let me write it this way. We have 3 collinear points, in which case, you can find a labeling that breaks things, right? So I could put a minus plus minus. I don't care about the label of the 4th point. So this cannot be shattered. Now, if 3 of them are not collinear, then one of 2 things can happen. Either 3 form a triangle. If 3 of them are not collinear, they form a triangle, right? That's clearly true. The 4th point can lie inside, or the 4th point can lie outside. Now what happens, I'm going to just put them in separate cases. So this is 3 of them are collinear, and 3 no. And then you have 2 cases. What would you do in the top case here, this one here? Sorry?
Give positive label to the middle one.
Give positive label to the middle one. And negative everywhere else. This cannot be shattered. The way to think about it is you have 3 points, you take the convex hull of all the points. The convex hull is basically simply a geometric object that like the tightest geometric object that contains all of them. It's just, in this case, fancy words for triangle. You label all the points on the triangle as positive or negative, and you give one label to all the points on the triangle and the opposite label to the point inside, and basically that breaks things. if 3 points, if the convex hull does not contain the fourth point, I can try to making triangles in any way I want. The fourth point is not going to be inside, but this is basically the XOR case, and that was the argument that came up before. So between the two of you, I think you got the whole proof. So this is the XOR case. I can do plus minus, cannot be shattered. So we have exhausted. Is there any other way to arrange 4 points on a plane? Is there any other possibility? Yes.
All four could be.
But if all 4 are collinear, 3 are collinear. So that takes care of this. You had a
4 points are collinear and 2 are positive equilibrium and then minus 1
oh yeah, sure. 4 points are collinear, cannot be broken also. But we don't have to think about that because we've already broken 3. If 4 are collinear, then 3 are collinear, we've broken 3. So we don't need to worry about that other case. But yes, that's another, if you had to, you could do that. Any other, are there other arrangements of 4 points on the plane? Now, yes. We are assuming 4, no, think of it as a set. It's a set of 4 points. Remember, shattering is defined for a set of points. There is no other way of organizing 4 points on a plane because we've exhausted everything. Either 3 of them are collinear, which covers one kind of arrangement, or 3 of them are not. If 3 of them are not, you can draw a convex hull around 3 of them. Either the 4th point lies inside, that's up there, or the 4th point does not. And these are the only possible things that we can do. So what this means is that for 4 points, no matter how you try to label them, 4 points cannot be shattered. Sorry, no matter how you try to place the 4 points, 4 points cannot be shattered. Remember, this is different from 3 points. For 3 points, there are some arrangements of 3 points that can be shattered. There are some arrangements of 3 that cannot. But with 4, no such luck. Questions?
At some point, can you just explicitly say what is arrangement and what is partition? So I feel in each arrangement there can be different labeling happening.
So an arrangement of the points, arrangement is just an informal term. What I mean by that is just given a set of points from the instance space. I call it arrangement because it's visually, you can arrange the points. Arrangement is simply saying, given a set of points, the definition does not say anything about arrangement. It's just given a set of points, we can blah blah blah, the rest of it. By partition, what I mean is for that particular set of points, you are dividing some of them into, labeling some of them as positive and some of them as negative. You're taking a subset of that set and calling it as positive.
So does the arrangement correspond to geometric positions of the set?
In this particular case. But really the instance space here is all points in the 2D space, and by arrangement I mean basically selecting 4 points or 3 points or whatever number of points, subset of that, finite subset. So I say arrangement is something that seems to work for if you have a geometric space, but if you have, say, documents, if your instance space is documents, it's no longer, then the argument should be a finite subset of that space, of the instance space, which is some number of some documents. Other questions? But partition is simply specifically saying that you have a set of points and I take a subset of them and call them positive, and I call all of them negative. all the others negative, sorry. I take a subset, call it positive, I call everything else negative. So in some sense, you can think of shattering as this sort of an adversarial game. There is you playing the game with an adversary. What you have is you claim you have a hypothesis space, and you claim that your hypothesis space can shatter these particular 4 points, or these particular d points, some number of points. And the adversary says, not really, here's a certain labeling that makes your points fit. By producing a labeling, by producing a partition. But then if that's what the adversary thinks, you can produce a function that correctly predicts all the labels, which means the adversary has failed. It's an adversarial game because the adversary is trying to beat you by producing the labeling that forces you to give up, and your job is to find the classifier that forces the adversary to lose. In this case, I have, following most comic book sort of situations, you have won, and the adversary comes back with a different thing. But that's not. With linear classifiers, the adversary wins with 4 points. I used to have a slide here with Batman and Joker, but that gets dated very quickly. Anyway, so it's an adversarial game. You claim that a particular set of points can be shattered, and the adversary's job is to find a labeling that forces your, both of you know the hypothesis space, that forces your hypothesis space to lose, and by lose I mean there is no function in your hypothesis space that can agree with the adversary's labeling, and your job is to find that function. And if you fail, the points cannot be shattered. If the adversary fails, the points can be shattered. Now, it turns out that some functions are actually so expressive that they can shatter infinite points. What that means is that this game can be played with an arbitrary number of points, and the hypothesis space can assign a labeling for that. And there are some, these are very interesting functions here in this class. One of them we'll see later on. It's the class of functions that are nearest neighbors classifiers. It turns out they can shatter infinite points. The way to think about it is, if your hypothesis space is completely unbiased, what that means is there are no assumptions in designing the hypothesis space. Then it can essentially predict it contains every function. It contains every possible labeling of all points that can exist. Now, if the set of points that can be shattered is larger, that means your function space is more expressive. The more expressive means there is less bias or less information guiding the design of the hypothesis space. So, in some sense, a richer class of functions can shatter more points. A more restricted class of functions can shatter fewer points. And why would you choose a more restricted class of functions? Because you believe that that's enough. You believe that your problem is simple enough that maybe linear classifiers are good enough. You don't need those weird squiggly lines. That's the intuition here. A richer class of functions can shatter more points. And that's the intuition that was formalized into the definition of the Vapnik-Chermanin-Kiss dimension, the VC dimension. Remember that I'm going to introduce this definition, but I just want to restate the definition of what it means for a function class to shatter a set. Given a set of points, it is shattered by a class of functions H if every partition of that class of the set of points can be matched by some function in that class. We saw the example so far. The VC dimension of a hypothesis space, we are no longer talking about a class of points. We are talking about a property of functions. The VC dimension of a hypothesis space is simply the size of the largest number of points that can be shattered. the largest finite set, the subset of the instance space that can be shattered by the hypothesis space is called the VC dimension. So, what does largest mean? If there is any subset of size d that can be shattered, that means the VC dimension is at least p. If no subset of the instance space of size d can be shattered, then the VC dimension is less than p. That's, in some sense, the definition of the largest. But there is a subtlety hiding here, which we encountered in the linear classifiers. So what we have actually been proving so far is that essentially we see dimensions. For half intervals, the half intervals are these things that are things like this. Half intervals can shatter one point. There is at least one set consisting of one point that can be shattered. There was that one set that I had on the thing, on the slide. So half intervals can be shattered. Half intervals can shatter one point, but half intervals cannot shatter 2 points, which means the VC dimension of half intervals is 1. Intervals can shatter 2 points. There is at least one set of 2 points that can be shattered, but no collection of 3 points can be shattered, which means the VC dimension of intervals is 2. For linear classifiers, or half spaces on the plane, things get more interesting. There is a data set of size 3, the triangle, that can be shattered. There is no data set of size 4 that can be shattered, because you can have 3 points like this, you can have a point like this, or you can have 2 points like this. This covers all cases. So there is a data set of size 3 that can be shattered, and no data set of size 4 can be shattered, which means the VC dimension of half spaces is 3. At this point, there must be a question. Yes?
I'm confused because there is a data set of size 3 that cannot be shattered.
Exactly, that is the question. There is a data set of size 3 that cannot be shattered. Right? That is a bit weird. But now let's go back to the definition. If there exists any subset of that size that can be shattered, the VC dimension is more than that. Even one set of points that can be shattered is enough to make the VC dimension more than 8. Yes?
Why can't we just arrange the points in word space?
In what?
And why can't we arrange 4 points to be shattered?
Oh, because we just exhausted. Every possible arrangement of 4 points cannot be shattered. That was the thing. These are the only ways in which 4 points can be arranged.
I thought these are. We show that there is an arrangement of 4 points that cannot be shattered, but there is still some possibilities of 4 points that can be shattered.
Show me.
Like if instead of XOR, it's, instead of a parity, you don't have a parity.
Okay. I'm glad you brought that up, because this is the first and somewhat confusing thing. Let's look at the definition of shattering. So, for a given arrangement, for a given subset of points, I'm going to stop saying arrangement. For a given set of points, for it to be considered shattered, every labeling must be matched. It's not enough for one. So, of course, with 4 points can be matched. But it's not enough to match one labeling, every labeling. So, this is where it gets complicated. Let me go to the VC dimension thing again and just add a page below. So for shattering, it is a property of a set of points, right? So we are given a set S is a set, and for this, every partition some function in the hypothesis space. But the key point here is that it's not enough to show one that can be matched. Everyone should be matched, and that's when we consider the set to be shattered. Now, for the VC dimension, and so really there's a universal quantification over the partitions. Here, if one, let me, there exists even one set of size P, if there's even one set that can be shattered, this is an existential quantification. If even one set can be shattered, then the VC dimension is more than D. What this means is, for this one set to be shattered, for that one set you have to try out every label, every partition. When I said 4 points cannot be shattered, we considered every possible labeling of 4 points and found examples that cannot be matched. So there is a universal quantification to prove shattering of a set. There's an existential quantification to prove this thing. So this can get a little bit tricky. And in the past, I used to write down this definition using logic with universal and existential and universal and existential. It kind of alternates, and that's not fun. I find it fun, but the class does not. But in some sense, what you should keep in mind is that this requires just a certificate in the form of one set of points that cannot be shattered. That requires an exhaustion of the labelings. Every single label should be matched. Even if one of them does not work, then it's not shattered. Yeah.
So we're finding all these subsets. Are there like different, I don't know, I guess maybe in this example, would there be different ways that we could classify our subsets that would have...
In some sense, that's what we need to do, and that's what we did for the linear classifiers, right? Here, we classified our subsets into three groups, and said there is no other arrangement of 4 points. And inside the subset, what we really should have done, which I did not do, what we really should have done is enumerated every possible labeling of these 4 points. Some of those labelings would work, but if it works, that's not good enough. We need to exhaust every single one of them and show every one of them works. Does that?
Yeah.
So, what we managed to prove is VC dimension of half intervals is 1, of intervals is 2, of half spaces on a plane, the VC dimension is 3. Half spaces on a plane is the weird case where you have to kind of think about the case where some certain labeling, some arrangement of 3 points can actually be, cannot be shattered, but that's not enough. Even if you are able to produce this one certificate, one collection of 3 points that is shattered, so VC dimension is more than 3. There are a few other results. I'm not going to prove it, but it turns out if you extend linear classifiers, yes. Yes. Yeah, but again, that's the same thing. If you have these 4 points, remember the definition of shattering requires you to exhaust all possible. The collection of points. There is at least one collection of points can be shattered, life is good. This collection of points cannot be shattered because I can produce a labeling, namely this, that breaks things. Yes?
So to clarify, for every subset of that dimension space, we can, of that constant class, we can pick the label, or we can pick the position of the dots.
In order to show that it can be shattered. Yeah. Yes, that's exactly right. In order to show that something can be shattered, it's another layer of adversarial, another adversarial game. You get to pick the points. In this case, for 3, I pick these 3 points. I pick the points and I show that these 3 points can be shattered. When I say that it cannot be shattered, no matter how I pick the 4 points, you can pick a labeling that makes me fail. So your job is to show that these 4 cannot be shattered. In which case, what you would do is pick a labeling that forces it to not agree. So think of it as 2 parties in this game. There is me, who wants to prove that the VC dimension is 4, suppose. Which means that I will pick 4 points. And you, who wants to prove that the VC dimension is not 4. Which means when I pick 4 points here, you get to choose a labeling. And if you can produce even one labeling that fails, then the thing fails. Because universal quantification requires every single thing to work. So you can pick a labeling here that makes it fail. VC dimension is less than 4. But maybe, if you can pick a labeling that makes all 3 of these fail, then the VC dimension is not 4. Does that make sense? I want you to kind of revisit this, work out the examples again by yourself, and in particular pay close heed to the definitions. If this does not convince you, there are homework questions. Your next homework will be about VC dimensions. You'll be proving some VC dimensions. And that will force you to kind of revisit these things. And we can kind of come back to this. It turns out for linear classifiers in D dimensions, the VC dimension is D plus 1, the dimensionality plus 1. Roughly for neural networks, we've not yet covered neural networks, but roughly for neural networks, the VC dimension is order of the number of parameters. For nearest neighbors, the VC dimension is infinite. It turns out, very, very loosely speaking, the VC dimension tends to look like the number of parameters you need to train. So, for a linear classifier in D dimensions, you have D plus 1 parameters, right? There's the weight and the bias. And the VC dimension is D plus 1. Now, with neural networks, there are some complications involving optimization. We'll get to that later. The nearest neighbors, we've not yet covered nearest neighbors. It's in some sense the easiest learning algorithm you'll ever see. That's why I've decided to put it all the way at the end of the semester. Once we get to that, try to prove that the VC dimension of nearest neighbors is infinite. It's a fun exercise. Now, I've spent almost the last hour talking about VC dimensions without actually ever telling you why it's interesting. Or rather, I've told you why it's interesting. More complex functions have higher VC dimension, but it turns out it has a very close connection to PAC theory. We talked about sample complexity, right? The number of examples needed for you to prove that with high probability you'll get a good classifier. We had this Occam's razor theorem, both in the case where the hypothesis space contains the true concept and in the agnostic case where the hypothesis space may not contain the true concept. In both cases, it turns out the complexity of learning, the sample complexity, essentially depended on the size of the hypothesis space. For infinite hypothesis spaces, like all the stuff that we've been looking at today, the VC dimension essentially behaves like the log of the size of the hypothesis space. I'm not going to prove any of these results, and I don't expect you to remember these things because they are annoying. But it turns out that if you want, you can prove these things. There are references that I have on the class website. If you have, say, a sample set with a data set with m examples, and you find, using whatever learning algorithm, I don't care, you find a classifier that is consistent with all m of them. If it turns out that the m that you have, the number of examples you have, is more than this quantity, there is like a lot of complication here, but really the thing I want you to focus on is this. If it is more than some number that is roughly linear, that is linear in the VC dimension, then with probability at least 1 minus delta, high probability, you have a classifier that whose generalization error is less than epsilon. This is why we went through this whole process of introducing VC dimensions, because if in the previous case, in the finite hypothesis classes, we had to look at the number of functions that we have. Here, given a class of functions, you have to measure the VC dimension. If the VC dimension is polynomial in the dimensionality, then the concept class is PAC learnable. Of course, you still need to invent a learning algorithm. I mean, it's not enough to just say that it's PAC learnable. You need to invent a learning algorithm that can actually do this, find hypotheses, but the concept class is PAC learnable if you have a polynomial VC dimension. This is in the case where your hypothesis space is consistent. This is like the consistent learning case that we saw. That was the first thing that we saw. If it turns out we move to the agnostic learning setting, where there is no hypothesis that's consistent with your data set, we still have a similar sort of a result. I have rewritten this, I've written this in a different form here. If you have m examples, then with probability 1 minus delta, the true error, the generalization error here of your hypothesis is bounded by the training error plus something that looks rather obnoxious. But really the interesting part here are how the VC dimension. The VC dimension is essentially polynomial. It is VC log VC. Which means that once again, you need to compute the VC dimension of a hypothesis space, and in the agnostic learning setting, you just have to, if that quantity is, if the VC dimension is polynomial in the dimensionality, then your concept class is PAC learning. What you have is a PAC learning guarantee. This is why VC dimensions are interesting. Essentially, it behaves like a measure of complexity of hypothesis spaces that are infinite. And we can prove the same kinds of bounds that we had. So, let me just, you have 4 cases. So you have a finite hypothesis space, or let's just call it finite edge, and infinite edge. Here you have H is a superset of C, and not a superset of C. These are the 4 cases that we have. If you want a chronological order of how we covered things, first we looked at this, then we looked at this. This is agnostic. In fact, this is agnostic. We looked at this, the first thing we looked at it before the fall break. Number 2, we looked at it on Tuesday, and both of these, I didn't prove anything, but I just showed you results. It turns out, in this case, the thing to worry about, the complexity parameter, is log of the size of the hypothesis space. Here also, it is the log of the size of the hypothesis space. Here, it is the VC dimension. Here, it is the VC dimension. If you can measure the VC dimension of the hypothesis space, then in both the I forget what's the name for that. When the H is a superset of C, and in the agnostic learning case, if your VC dimension is polynomial in the dimensionality, life is good. If not, life is not good. There are function classes where the VC dimension is not polynomial. There are function classes where the VC dimension is infinite. In fact, what we have here really is an Occam's result. Both of these. Let me just show you this for example. If you want your generalization error to be tightly bounded by very close to the training error, then you're better off finding a classifier, a hypothesis space that has low VC dimension. Because the thing inside the box gets smaller as the VC dimension gets smaller. It's an Occam's razor result that says prefer hypothesis spaces that have low VC dimension. VC dimension is in some sense the measure of complexity. So once again, we have an Occam's razor result, except here the measure of complexity is not the size but the VC dimension. Here also there's a Occam's razor result, because if your VC dimension is small, then you can get away with a smaller number of training examples to have these guarantees. So once again, there is a reason to prefer simplicity. Of course, I call it simplicity, really there's a reason to prefer smaller VC dimensions. Questions? Yes?
You had an example of BC being able to be in infinity.
One nearest neighbors. Yes.
Yeah, so that's going to kind of
I know.
fall off the map
It is. So if you want to prove generalization bound for one nearest neighbors, you're out of luck. And that's a fantastic question, because that also says something is weird about the theory, because nearest neighbors works. So this is a worst case result. In the worst case, life could be bad. But real life maybe is not worst case. That seems to be the consensus. Deep neural networks, for example, are off the charts when it comes to VC dimension, because it's a number of parameters, and we train classifiers, we routinely train models that have millions and millions of parameters. Everything, all intuition that we built up with this theory says that deep learning should not work. And yet we can, have self-driving cars. So again, this is one of those kind of uncomfortable places where the best we know about learning theory seems to fall short, because learning theory is inherently a worst case kind of a situation, whereas average case doesn't seem to be that bad, and we don't have the tools to deal with that. And if any of you are interested in building a career in learning theory, that's the question, that's one of the important questions that's worth thinking about. Other questions?
So I think Boolean conjunctions, the log of that is n, and then linear threshold units is also n. So why are you saying that linear threshold units are still easier?
Oh, it's not easier. Linear threshold units are more general purpose. It's a pragmatic thing. If you did not know that the classifier, the true concept was a conjunction, that's a very insightful observation. I've never thought of that actually. So let me just restate that for the class. For Boolean conjunctions, the log of the size of the hypothesis space is order of n. For linear classifiers in n dimensions, the VC dimension is also order of n. And I keep saying why linear classifiers are a better thing to have than training in Boolean conjunction, a classifier for a learning algorithm for conjunctions. The reason I think is more pragmatic. If I have an algorithm for learning linear classifiers, I have not just covered conjunctions, I've covered conjunctions, disjunctions, M of n functions, and other things. If I have an algorithm for learning conjunctions, I have an algorithm for learning conjunctions. Which means that I am making a stronger assumption if I'm using that algorithm for learning conjunctions. If I'm using an algorithm for learning linear classifiers, I'm saying I don't know that I'm learning conjunctions. All I know is it's linearly separable. So I'm exploring a larger class of things. Yeah, that's actually a very interesting point. I wish I had thought of that, because I would have put that in the exam. I tried. Anyway, so as an exercise, what I want you to think about is we never, nothing in VC dimensions or shattering ever said anything about whether the function class is infinite or finite. Everything was about, if I give you a set of points, if I get you a subset of the instant space, it can be shattered or cannot be shattered. And that talks about labelings. It does not talk about infinities at all. It completely, very cleanly sidesteps the idea of infinite functions. Which means that the same definition could in theory be applied for finite concept classes. What I would like you to think about is, what is the VC dimension of a finite concept class? Any finite concept class. Start with something that you can think about, like conjunctions, and then move to arbitrary concept classes. There's some possibility that this question might even show up in your homework. Your next homework, in fact, will also ask you to compute the VC dimension of different classes of functions. Imagine, for example, remember we started the whole class, the lecture today, with these rectangles. What's the VC dimension of rectangles? Think about it. And the usual sort of procedure for computing VC dimensions is you start off with one point. Consider one point placed on a plane and assign all possible labels, and can you find a rectangle that puts a plus around the point, or around the point that can put a minus? Can you find a rectangle that can contain the point? Can you find a rectangle that can be such that the point is outside the rectangle? So one point can be shattered. Now consider 2 points, consider 3 points, consider 4 points. You get to pick the position of the points, so try to find a point which can be shattered, a collection of points that can be shattered. You keep going up until you come to a number of points where no matter how you place the points, no rectangle correctly classifies it. At that point, you have to write down a proof, like the thing we did for the linear classifiers. You need to exhaust all possible positions of certain number of points, where no matter where those 5 points or 6 points or 8 points are, you will be able to find a labeling that the rectangle cannot correctly classify. That's the general structure of the proof. Now, so this is going to be the end of our computational learning theory part of the class, and starting next Tuesday, we'll go back to the algorithmic things. One thing that I would like to point out is, what you need to know with learning theory is you need to know what is PAC learning, you need to know the definition. This is in some sense the dominant theory of learning. You need to know consider, we looked at 2 possible cases, finite and infinite hypothesis classes. You need to know what is, essentially the intuition that the size of the hypothesis class is the complexity parameter. You need to know what's the sample complexity and all that. You need to be able to derive everything for finite hypothesis classes. And also, just like you did for with the halving theorem kind of halving algorithm kind of thing, you need to count the size of the hypothesis classes. I'll give you a set of functions, or think about a set of functions. You need to be able to say how many functions are there. For infinite hypothesis classes, essentially the complexity parameter is the VC dimension, and you need to know what VC dimension is conceptually. And it can get tricky, and I encourage you to go back and revisit this whole thing and seriously work the examples, the small examples. The annoyance about this definition is this sort of an adversarial thing you have for every set of points, for every set of labels, and it gets a little tricky. So you need to be able to find the VC dimensions for simple classes of functions. And you need to know that higher VC dimension means more sample complexity. So the VC dimension functions like log of the size of the hypothesis class. Now, computational learning theory is in some sense the theory of generalization. When we started off, we started looking at, when you give me an algorithm, how can I trust it? The answer is, you need to think about what classes of functions does that algorithm explore. If that class of functions is small enough, if it's simple enough, then you can start playing the PAC game. And PAC learning is the theory that tells us that if you have, how many examples do you need in order to guarantee that with high probability, you've got a good enough classifier. Now, it turns out this theory answers, this way of thinking answers theoretical questions like, what does learning mean? How good is my class of functions? Why should I use one concept rather than other? Is a certain concept learnable at all? What does that mean? If it is learnable, how many examples do I need to get a good enough approximation? We looked at mistake bounds as a way of answering similar questions in the past. A very, very cool thing is that if you can prove that something is a mistake bound algorithm, mistake bound learnability implies PAC learnability. So there are generic online to batch conversion schemes, essentially like the thing where you do multiple epochs over the data, that give you PAC learnability. It also raises very interesting theoretical questions, and these are actually two theoretical questions that followed the idea of PAC learning was introduced in 1984 in this paper called The Theory of Learnable. I encourage you to read it. It should be accessible to you right now. We've covered a lot of examples from that paper actually. Very quickly after that, some interesting theoretical questions were raised. If a concept class is weakly learnable, however you think of weak learnability, does this mean that it is strongly learnable? Weak learnability is there is a learning algorithm that can produce a classifier that is always slightly better than chance, but only slightly better than chance. Does this mean you can actually get this concept class is strongly learnable in the PAC sense? Essentially, if you have rules of thumb that seems to work in real life, does this mean that the concept class is learnable? Another theoretical question that came up is, we have seen these bounds where the true error is training error plus some ugly term, involving AC dimensions. Can we use this criterion by minimizing this quantity here to minimize the generalization error? The answer to the first question gives us something called boosting, because some of you may have heard of boosting. It was actually motivated by PAC learning. The answer to the second question gives us this principle called the structural risk minimization or empirical risk minimization principle, which is essentially the dominant way of designing learning algorithms today. And the concrete example that we will look at, that's the direct offshoot of that, is the support vector machine. So in the next lecture, we'll look at boosting. After we finish that, we'll go to SVM. Alright, I'm a minute over time, so I will stop.